Okay, so that was part one. Here's part two. I definitely went over on part one, so let me try to keep part two a little shorter. In part one, we came up with this very simplistic model um, of growth for COVID-19, where we said it doubles every 3 days. So we could write this model that says y is the number of people infected, right? Um, and we could model the number of people infected by saying that y is equal to 1, starting with one person, times 2, we double that every 3 days. So x is the number of times we've doubled um, the number of 3-day periods. And you could look at the data and actually show that. So for example, I just clicked on, let's say, 313 here. On 313, there were 2,000 people infected. And if we go forward by 3 days, that number should be doubling. So if we had started with 2,000 people, let me see, 1, 2, 3. 3 days later, there were 4,000 people. And if we go forward 3 days again, we should double that number again. So 4,000 people, and we go forward 3 days. 1, 2, 3. Ooh, there were actually 15,000. Actually grew by more than double. And you should be able to do this. Look at any part of the beginning of this data, and it should follow something similar. So let me see. Here's 10,000 people infected. Let me go forward 3 days. 1, 2, 3, and sure enough, there was about over 20,000 people. So it's more than doubled. But simplistically, this is kind of our simplistic model here for the growth of coronavirus in the beginning, based on what our medical experts said. So let's take that model and move on and say, okay, we got sent home from school on March 13th. How many days had it been since the first case was confirmed? So we got to do a little bit of math here, a little bit of thinking. Let's see. We're saying that the first case, right, was on January, what did I say, 21st? January 21. So how many days were left in January after that? Well, there's 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So there were 10 days, right? 10 days left in January. I'm trying to figure out what number do we plug in for x here, because we want to know how many people were infected based on that by the time we close school. So how many days has been, how many 3-day periods is that? So let's see, there were 10 days in January. This is in January. Plus, how many days in February? How many days were in February this year? And don't forget, this year is a leap year, so normally there's 28 days in February. This year there were 29. And then March 13th. So we're saying there were 13 days. We were 13 days into March, right? So we had 10 days left in January, 29 days in February, and 13 days by March 13th. So what is 10 plus 29 plus 13? Let me go here. I don't like to do arithmetic myself. 9 plus 13, that means there were 52 days. We were 52 days into the virus, having started in the US. 52 days. But remember, in our model, we don't care about maybe exactly how many days it's been. We care about how many 3-day periods it has been. So let me take that and then divide it by 3. 52 divided by 3 equals, let me do this again, divided by 3, 17, about 17 periods of growth, of doubling. I can write a little squiggly line here. 17 periods, 3-day periods. So we're saying, according to our model, it should have doubled 17 times. So how many people were infected by then? Well, let me plug that in here. So let's see, y is equal to 1 times 2, right? That's our doubling. How many times has it doubled? 17 times. We should have been doubling. So how many people, according to this model, were infected? Let me throw that in here. Say 1 times 2, power of 17. 131,072 people. Wow. 72, right? Yeah. 131,072 people, according to our simplistic model of doubling every 3 days. In reality, how many people had been infected by then? Well, let me take a look at the data here. March 13th. Actually, our data, our model's off because we only had about 1,896, about 1,900 people. In reality, it was far less than that. It was about 2,000. It was only about 2,000 people. So, our model might not be perfect. Maybe it had slowed down a little bit from that initial doubling every 3 days. Or maybe our first day we should have started the doubling maybe wasn't the very first day that somebody was infected. A lot of things can go wrong in modeling. Let's keep going though. So when does our model predict the number of people infected would reach 10,000? How many days would it have been? So let's see. The question here is, when is y in our model, which is equal to 1 times 2 to the x, right? When is this going to equal 10,000? It looks like it's before 17 time doubling. So the question is, what does x have to be? What is this, right? That's what we're wondering. What is x going to have to be? So I think it's going to be less than 17 doubling, because at 17 we were at 131,000 already. Let's plug in. Let's try something. Let's try 1 times 2 to the power of say 12. We're looking for 10,000, right? That's 4,000. So let's do one more time. It'll double to 8,000. So one more time should double that to 16,000. So 14 times we have to double to get to 16,000. So let me say x would have to be 14. It would have to double 14 times to get past 10,000. So if it doubled 14 times, how many days is that? Well, remember, x represents every 3 days. So 14 times 3 means how many days have actually gone by? 42 days. So 42 days in, our model says the number would reach 10,000. And you could do the same thing with 100,000. When is this going to reach 100,000? It's probably day 16, right? Or not day 16, but the 16th time, because by the 17th time we've already reached it. Although half of that, the previous will be half of this, so maybe it's actually the 17th time. It reaches 100,000. So x equals 17 from up here, 17 times, which means how many days have gone by? Well, you do 17 times 3, and I think it'll probably be about 52 days. 17 times 3 equals, how many days would that have been? 51 days. 51 days. And then lastly, how many times would it have to double to reach 1,000,000 people? When is this going to equal, starting with one person, when would this equal 1,000,000? What would x have to be? Well, we could plug it in. We could try some things. Take a guess. Take a guess. What do you think it would have to be? Times 2 to what power? How many times would you have to double to get to 1,000,000? At 14, we're 16,000. At 17, we're at 131,000. What do you think to get to 1,000,000? You're probably going to overshoot it. I'm thinking it's only going to be like 20 times. Yeah, actually, it looks pretty close. 19, yeah, 500,000. Yeah, 20 times we reach 1,000,000. At x equals 20 times. It only needs to double 20 times to reach 1,000,000. So how many days would that be? Well, let's see. 20 times 3 days. That's 60. 60 days in our model. Our model says that after 60 days we'll reach 1,000,000 people. Now, is that true? I don't know. We could look at our data here. Let's see. When did it reach 1,000,000 people? It looks like actually it didn't reach 1,000,000 until the end of April. So this was 52 days in the middle of March. You have to add another 30, 40. So really it took like maybe 90 days to reach that level, right? Is that right? April has 30, so we'd have to add 30 more, so that's 80. Yeah, maybe 90 to 100 days. In reality, it took 90 to 100 days. So our model's predicting a faster growth than what actually happened. Why is that? Well, we'll look at that in part 3.